Hi, welcome back to the Astro Imaging channel. Glad you were all able to come back after our exciting program last week. Tonight we have Jim Thompson, who's going to talk to us about solar imaging. I thought maybe I knew what this was going to be about, but I saw a couple of slides and I don't think I do. So this is going to be really, really interesting. And of course, next week, I'm not going to bring up the calendar, but next week is the NEAC meeting, so we won't have a show. And after that, Paul Smedwick is going to give presentations on the trials and tribulations of setting up remote imaging. Some of us have been through. Paul, you want to give us a little preview of what you're going to do about?
Yes, yes, I will. My name is Paul Smedwick. I've recently been a member of Starfront Observatories. I've been there since October of last year. So I'm going to quickly share my screen here. 1 second. 1 second. Entire screen share. And I am, so basically my journey is going to start with remote observatory and Idiot's Guide having the remote. So I will be going through my whole process and pains and agonies and frustrations on how I get started. I thought I knew a lot before I went in. I learned a bunch more. So I will explain you the journey that I went through, give you some pointers if you're very interested, and what you have to keep in mind for remote hosting. So it should be exciting. It's kind of it'll be kind of a funny type of a hilarious type of presentation, make fun of myself, but I think you can gain some great knowledge from that. Thank you.
Yeah, I think that we all believe that, we envy, if we don't do remote imaging, we envy those dark skies and the multiple nights. And we say, we just put a telescope there and turn it on and everything is just hunky. That's anything but the truth. And I'm sure Paul's experience and her humor will be a nice presentation in a couple weeks after NEAC. And of course, we always want to get more people for the Astro Imaging channel. We have some open sessions coming up in like 3 weeks. If you have an idea and you would think that your ideas would be something you'd like to share, please send us a note. Go to the astroimagingchannel.org. There's a little contact form. Give us an idea what you want to present. Someone will get back to you. And don't think that it's all been covered before, because every month, every 2 months, there are new things coming out, or you may have developed something new that you would want to share with us. Be bold, get out there, let us know, and it'll be you on the Astro Imaging channel. And with that introduction, Jim, you want to tell us about your solar imaging setup?
Absolutely. I'm just going to share my screen. So you should be able to see my slides.
You are good.
Excellent. Well, welcome everybody to my talk tonight titled Supersizing Your Solar Setup. Before I get too far into it, I'll introduce myself to you all in case you don't know who I am. I acquired my passion for astronomy growing up under the dark skies of Eastern Ontario cottage country. I have a master's degree in aerospace engineering and have been working for almost 29 years at an Ottawa defense company called Davis Engineering. I primarily observe from my Ottawa Bortle 9+ backyard, which is why I am a strong advocate for electronically assisted astronomy. And this is the main impetus for me becoming somewhat of an expert on astronomical filters, which I gave a talk on, was more than a year ago, I think now. One area of amateur astronomy that I greatly enjoy is solar imaging, which is what I'm going to talk to you about this evening. Interest in the sun has seen a sharp increase in the last couple of years. This is due both to the steadily increasing solar activity, as well as the 2 recent solar eclipses that we saw, partial in October 2023, and then, of course, the beautiful total eclipse that we had last April. I suspect a large number of you already have invested in at least some rudimentary solar observing capability. Tonight, I will present a review of the many different products available for enhancing your solar experience, many of which can simply be added to your existing setup. I originally gave this talk to my local astronomy group back in November, but since then I have added some new material on spectroheliographs, so stay tuned for that. Now let's do a quick review of what it is exactly we're trying to observe. The sun is made up of various layers. The outer 1/4 is called the convective zone, a layer displaying a rapid conveyance of energy from the interior out to the surface. We can't view the convective zone directly, but we can observe its impact on the layers above. The first layer we can observe is the 500 kilometers thick photosphere. I apologize for the metric units. I'm Canadian, so that's all I know. This is the point where the temperature has dropped low enough for the electrons to recombine with their atomic nuclei, and for photons from the interior to travel unhindered out into space. Above this layer is the 2,000 kilometer thick chromosphere. In this layer, the sun's magnetic field transfers energy back into the gases, making up the layer, reionizing them and moving them around in beautiful but complex ways. At the top of the chromosphere, there is a thin transition layer followed by the very large and very hot corona. The equipment I will discuss tonight is dedicated to observing the photosphere and the chromosphere layers from our vantage point here on Earth. So my review begins with what I call Level 1 photosphere observing. This can be accomplished using the rear projection method, where you use a small telescope or binoculars to project an image onto a white surface. The method is relatively easy and safe and can be done with your existing telescope or binoculars. With it, you can see sunspots, determine the sun's rotation rate, and track solar activity, just like scientists did in the 17th, 18th, and 19th centuries. But if you're looking for more in your solar observing, you can move to Level 2. This involves the use of filters over the front aperture of your telescope. These filters are made of polymer film or glass and can be purchased pre-built for your particular size of scope or build your own. The materials can be fragile, so it is important to routinely inspect these filters to ensure that they are safe to use. Using an aperture filter, you see more detail, including sunspots, granulation, and faculae. The views you get will be much sharper and detailed than with rear projection. To show you what I mean, I've prepared a couple of comparison images. The image on the left is the best picture I could find online from a rear projection setup. The other two images were captured by me last fall using a purchased glass filter on my 10-inch RC, you can see that in the middle, and a homemade Astro solar film filter on my 4-inch refractor, that's on the right. The aperture filters clearly produce much more detail, with the Astro solar filter film producing the best image of the three. So this isn't too bad. But what if we take it to Level 3? Level 3 involves the use of something called a Herschel wedge. The idea for this device was originally conceived by John Herschel in the 1830s. It uses a wedge-shaped prism to reject about 95% of the incoming energy out the back. There are several brands available today, all of which are meant for use on refractors less than 4 inches aperture. Larger than that, you'd need to add an additional energy rejection filter. Using a Herschel wedge, you can see pretty much the same things you can see with an aperture filter, but they provide superior sharpness, contrast, and detail. They also provide a much brighter image, so they pair well with filters. I prepared another comparison, this time between Astro solar film and a Herschel wedge. Same day, same telescope, same camera. The two images have very similar amounts of detail and sharpness. However, the wedge image on the right has noticeably more contrast. Note the large-scale patterns that are visible in the granulation with the wedge, but not in the film. This brings us to level 4, which is achieved through the addition of bandpass filters. Filters can greatly improve the performance of any of the previous levels, but note that filters darken your view, so they work best with a Herschel wedge. Filters allow you to see sharper images with more detail and contrast, and can help to mitigate bad seeing conditions. The string of lovely clear weather I had back in October last year has allowed me to prepare you some examples taken using different filters. The image in the upper left represents what you'd see with your naked eyes through a Herschel wedge, or your camera would see with a simple UV IR cut filter. The image has nice detail, but is a little blurry. Adding a solar continuum filter from Bader Planetarium sharpens the image and enhances contrast. The G-band filter from Altair Astro in the UK does much the same, but also enhances the visibility of faculae. That's the bright areas connecting in between the sunspots. For fun, I also tried an H-alpha filter meant for deep sky imaging, and the result was also beneficial, with image sharpness improved over the no-filter view. Note that all these images have been captured using a monochrome camera. If you are a visual observer, these filters will result in a view that is strongly colored, as noted in the square brackets next to each image. The last thing worth discussing is how much all these accessories cost. I have prepared a summary table for reference that includes most of the options available today. I apologize again for the use of Canadian dollars. Just divide by, multiply times 3/4 is about the US dollar. The most expensive things on the photosphere accessory list are Herschel wedges. But the main takeaway here is that for enhanced photosphere observing and imaging, we are talking about tens to hundreds of dollars. So not too bad. The same cannot be said for chromosphere observing. Level 1 chromosphere observing involves the use of calcium 2K filters. These are typically a filter added to your existing telescope setup, but they require some amount of energy rejection to be included as part of your setup, such as using a wedge or an aperture filter. Because the calcium K line is in the UV part of the spectrum, it is meant for observing using a camera, not your eyes. Using calcium K, we can see the lower chromosphere, complete with sunspots, megagranulation, plages, flares, and on a good day, prominences. Level 2 chromosphere observing requires the use of a very narrow band hydrogen alpha filter, specifically a device called an etalon, which delivers band passes narrower than 0.7 angstroms. The devices are tunable to account for Doppler shift of the fast-moving gases you are trying to observe. They are available in the form of dedicated solar telescopes or as add-ons to your existing refractor. With these devices, you can see the middle upper chromosphere, complete with sunspots, fibrils, spicules, plages, prominences, filaments, and flares, a veritable smorgasbord. Before showing you comparison images, I thought you might want to know more about how a hydrogen alpha solar telescope works. At the front of the scope, there is typically a red-colored energy rejection filter that knocks down a big chunk of the energy coming into the scope. Behind that is the etalon, a very accurately ground piece of flat glass with a semi-reflective coating on either side. Light wavelengths that are integer multiples of the glass thickness pass through the etalon by way of constructive light interference, while all other wavelengths are reflected away. This produces a response that looks like a comb, with many, many very narrow passbands. These bands can all be shifted down in wavelength by tilting the etalon relative to the incoming light, or by using some other means like temperature to change the effective thickness of the glass and thus the distance between the two semi-reflective surfaces. After the etalon comes the blocking filter, which has a precisely defined passband that allows only the one etalon band corresponding to hydrogen alpha to get through. Stacking these three filter components together gives you the single narrow passband you need for observing the chromosphere. As for the photosphere, I have also prepared some comparison images for chromosphere observing. The left two images were captured using calcium K filters of various bandwidths, 5 nanometers on the left, 2 and 2 in the middle. And the image on the right was captured using an H alpha setup that has one etalon, a so-called single stack. There is clearly an advantage to using a calcium K filter with a narrower band pass, as details are much better defined in the 2 nanometer image. Although there are many shared features between the calcium K and H alpha images, there is clearly a lot more going on in the H alpha image. These differences are further illustrated when we zoom in to the full resolution of the images. The active regions are well captured in calcium K, but the movement of chromospheric gases in the form of spicules, fibrils, and filaments is only visible in H alpha. So, what, pray tell, does level 3 chromosphere observing involve? Well, how about stacking 2 etalons together? Doing so further narrows the passband to less than 0.5 angstroms for an additional improvement in contrast. The narrower band reduces the brightness of the solar disk, allowing for dimmer features like filaments and prominences to stand out more. Using a double stack, you can see all the same things as with the single stack, but with more contrast and detail visible. It so happens that I purchased a second Etalon last June to form a double stack with my existing setup. These two images captured with my setup illustrate the differences: single stack on the left and double stack on the right. Notice how the solar disk is darker in the double stack image, resulting in an accentuation of the bright plages. That's these brighter areas around the sunspots. And also accentuation of the dark filaments. That's these stringy things that we see here. This effect is perhaps even more visible in these comparison images I took back in July. Also note in the double stack image how the sunspots are much less prominent. The double stack is more effective at blocking the light coming from the photosphere, allowing just chromospheric light to get to the observer. So not too shabby, really. However, as with most things in life, you can always go bigger. In this case, I'm talking about level 4 chromosphere observing. This involves moving up to scientific grade etalons or spectroheliographs. These devices give extremely precise and narrow band passes, and thus deliver superior contrast and detail. It is also possible to observe absorption lines other than calcium K and H-alpha, especially when we are talking about the spectroheliograph, which is the odd-looking device shown at right. Using these implements, one can see pretty much whatever they want, any aspect of the photosphere or chromosphere that is visible from Earth. I pulled a few example images from the internet to show what is possible. The image on the left was taken using a Daystar brand calcium H device on a 12-inch aperture refractor. The image in the middle is an H-alpha capture made using a Daystar quark on a 6-inch refractor under extremely steady conditions. And the image on the right is a helium-D3 emissions image captured using a do-it-yourself spectroheliograph called the Solex. In terms of cost, chromosphere observing is much more expensive than photosphere observing, by a factor of 10 or more. The reason for the large increase in cost is the requirement for difficult-to-manufacture high-precision filters and the machining that house them. It will be interesting to see if the trend toward high-quality but less expensive Chinese-made astronomy equipment that we have seen in recent years eventually makes its way into the solar observing market. As you can see on the list here, Chinese filter manufacturer Antlia has recently entered the market with a number of different calcium K filters. Acuter and Skywatcher, they have some new solar scopes, which are also relatively recent additions to the list of available equipment for photosphere observing and imaging. So that's the end of my main part. But before we move into the next section, are there any questions?
Jim, I have a question. You mentioned earlier with small refractors, you didn't use an ERF. So don't you have a tremendous amount of heat? You're pointing towards the sun, and you might be doing that for an hour or two, and getting trapped inside a refractor isn't necessarily a good thing.
That's a good question. So that relates to the recommendation to only use a wedge with a 4-inch refractor or smaller. The dangerous aspect of focusing the light of the sun through your telescope is in the area where the beam of light is near focus. So typically that is outside of the refractor, especially in the case of when you're using a wedge, because it adds quite a lot to the back focus of the telescope. So because the sunlight within the scope is well out of focus, the flux through an area is small enough that the temperatures are manageable. It does warm up somewhat, but the temperatures are manageable.
Okay, thank you.
You're welcome.
Jim, we do have a couple of questions coming in from people. Anak Chan, seems to be a strong emphasis on filters to reveal layers of detail. And Anak says he may have missed this, but how much does optical aperture play with respect to the resolution of the detail?
Just like it would for deep sky or lunar, the aperture of your scope does have an impact on what the smallest angular detail is that you can resolve. There is an issue with typically seeing being worse during the day. You have larger temperature gradients, so your seeing is worse. So typically seeing limits the minimum resolution that you're able to observe. So like where I am, sort of in the middle of the continent, where seeing is typically poor, there would be no point to me using a telescope larger than 4-inch aperture. I wouldn't be able to resolve, I wouldn't be able to take advantage of resolving capability of a larger scope because of my seeing conditions. But if you're in a very dry, steady location, then a larger refractor would be better, or could be better.
What time of the day, elevation of the sun, would you find most productive?
Well, I usually don't follow the rule of thumb. The rule of thumb is normally mid-morning. So before the sun has had time to heat up the earth is when you get the best seeing conditions. But for me, being at 45 degrees north latitude, I need to get it closer to noon, especially this time of year. In the summertime, I can do it in the morning and get better conditions. But yeah, in this time of year, I have no choice. I have to, it's a trade-off between looking through more atmosphere and getting steadier air. So for me, around noon is the best time. In the afternoon, the seeing gets progressively worse. So,
okay.
If I can just add something to that, as soon as you can see the sun in the morning, even though there's more atmosphere to go to, the scattering is generally in the blue, and the steadier the skies will be. There's no real rule of thumb, but by 10, 11 o'clock, it's over, especially with any kind of focal length. Instinctively, you would think, well, we should do it at noon. The sun is highest. That should be the best. If you take your DSO experience, you will quickly find that's wrong. As soon as you can catch that sun over the horizon, the steadier the sky, the less warming there will be, the less turbulence. Of course, if you have a full disk, it's not as much of an issue as if you have maybe a 3-meter scope trying to do it.
Okay, we're caught up in the questions coming in from the comment section, so you can proceed with the rest of your show, James.
All right, excellent. So this is the point in my talk when I crank the nerd level up to 11 and talk to you about spectroheliographs. The device was coincidentally invented simultaneously by 2 different scientists, George Ellery Hale, who is a famous solar scientist, and Henri Alexandre Deslandres in the 1890s. The device is designed to allow imaging of the sun at a single monochromatic wavelength of light that the user can select. These devices are still in use today by scientists, but more importantly, they are also within the reach of amateurs. So tonight I'm going to share with you some of my recent experiences with a commercially available spectroheliograph made by Astro called the SHG 700 that I purchased back in November. Amateur spectroheliographs really got going a number of years ago with French astronomer Christian Bruyl's design of the Solex, shown here, which uses 3D printed plastic components and optics available as a kit from various online suppliers. The design was greatly improved by Dr. Min Trong from Astro, including the use of a machined aluminum housing, precision optics, and fine focus and wavelength controls. Let's have a look inside the SHG 700 to see how it works. Starting at the right side of the image, light enters from the telescope and passes through a 7 millimeter tall by 7 micrometer wide slit. Thus, the device is taking a very thin slice of the sun to examine at a time. This slice is passed through a series of lenses to collimate the light and focus it onto the diffraction grating, which is at the left side. The grating spreads the slice of light out by wavelength, much like a prism does to sunlight. The user can rotate the grating to select what part of the sun's spectrum they want to project onto the camera sensor. The spectrum projected from the grating passes through a last set of lenses to focus the pattern onto the user's camera. Fine focus adjustments of the grating and the focus of the two lens packages are implemented using the micrometers installed on the other side of the unit. You can see the camera focus one there in the lower part of the image. Christian Bruyl's website has a great video to illustrate how one uses a spectroheliograph to capture an image of the sun. And I'm just going to switch over to that now. So here we have the spectroheliograph, much like the image we just looked at. Light is entering from the telescope. I'm not sure. Can you see my cursor moving around, by the way?
You're good.
Yes,
Yes,
You can see that? Okay,
can.
good,
Yeah.
excellent. So you can,
and Jim, remember, if you ask us a question, we've all been muted. So we have to run down and click on it. So we're here, okay?
Okay.
It just takes a few seconds to react.
no problem, no problem. All right, so we see here the beam of sunlight coming through the telescope, focused on the slit. So as we move the telescope across the face of the sun, this slit is going to move across. And the light from that slit is passing through the collimating lens, hits the diffraction grating, and then the spread out spectrum is what's kind of illustrated here to kind of show you what we're talking about. This white box here is the area of interest that the user has selected in their camera software. This dial over here represents the dial that's connected to the grating. And if I just manually move the video bar here, you see as we turn the dial, it rotates the grating and changes the part of the spectrum that is being projected into the area of interest on the camera. So we use that to select a particular absorption band of interest. I'm just going to keep advancing it here. So once we've selected the absorption band we want, we pan the telescope across the sun, which moves it across the slit. You see how the image is moving across a slit. The whole time we're recording a video. That's what's in the lower left corner there. That's the video sequence that's being saved in our camera software. And there, that's done. So that is what's happening when we take our data. Back. That one. So this is a single frame from the video that one would get from this process. In this case, it is an image of the sun spectrum in the area of the hydrogen alpha absorption line. That's the thick line across the middle of the frame, pointed out by the arrow. There are numerous other absorption lines visible, some from elements in the sun's atmosphere, like pointed out there, and others from elements in the Earth's atmosphere. They tend to be fainter and more numerous. Vertical lines that don't move during the scan are due to dust or small defects on the slit. Remember, the slit is only 7 micrometers wide, so a speck of dust on the slit is quite large. Vertical lines that do move from frame to frame are due to granulation on the sun's photosphere. A few other interesting features to note. The squiggly appearance of the hydrogen alpha absorption line is due to material in the chromosphere moving at different speeds, causing a Doppler shift of the absorption line. And this feature here, sticking out the sun's limb, is the appearance of the chromosphere viewed edge on and rising above the extent of the photosphere. Pretty darn cool, in my opinion. The last thing to note is that for my particular camera orientation, increasing wavelength is downward. One of the first things I just had to figure out with this new gizmo was how good a spectral resolution could it deliver. This is an excerpt of the sun's spectrum as captured by the Observatoire de la Tourbière in France, using a spectrometer that has a spectral resolving power of 30,000. This is my spectrum, scaled and rotated for comparison. Using the upper spectrum, I was able to identify several known absorption lines and their wavelengths. I was also able to measure the number of pixels in my image between 2 of the known absorption lines. Doing the math, my image has a spectral resolution of roughly 0.1 angstroms per pixel. Not too shabby. And on par, I'd say, with the upper spectrum captured by a professional observatory. Now let's have a closer look at that hydrogen alpha absorption line. Here it is again, but stretched out in wavelength so we can see details more clearly. During post-processing, the software will stack all the captured frames and find the polynomial that best fits through the center of the most prominent absorption line. That's the red dotted line I've shown here. The single row of pixels along this fitted curve is what the software will extract from each video frame to reconstruct the image of the sun. Each video frame being one column of pixels in the reconstructed image. There are a couple of different free software packages out there that do this, but the one I am using is called JSolX. and I like it quite a lot. It's easy to use. If you're wondering, a single stack etalon produces an image by averaging everything in this bandwidth, and a double stack everything in this bandwidth. So you get the idea of the difference in spectral resolution we're talking about. I have a feeling that you're all wondering, when am I going to stop flapping my gums and finally share an image generated using the spectroheliograph? Well, the wait is over. These 3 images were all captured a week ago from my urban backyard. The leftmost image captured using a single etalon, the middle with a double stacked etalon, and the rightmost image using the spectroheliograph, the SHG-700. The gradual increase in contrast in the chromosphere as one narrows their absorption bandwidth is pretty obvious. I find the active areas really stand out in the spectroheliograph image, as do filaments and prominences. The next images, perhaps, show this even better. These were captured 2 weeks ago when my seeing conditions were better. Now, I could end my presentation on this slide, but I don't know. The virtues of the spectroheliograph have already been pretty well described, but alas, there is so much more that you can do with this gizmo. It behooves me to tell you all about it. Remember that image of the hydrogen alpha line I showed you earlier? Well, hidden within this single frame is a plethora of data that can easily be accessed using the software tools available. For example, if we tell the software to move 3 pixels in wavelength down from the on-band line, about 0.3 angstroms, we can construct an image of hydrogen gas in the chromosphere that is moving towards us at a particular speed. As another example, we can tell the software to move 15 pixels, or about 1.5 angstroms, off-band to where there are no absorption lines, and construct an image of the photosphere. We are free to choose any arbitrary offset from the main absorption line, offering us a mind-boggling number of ways to view the sun. The first example I mentioned, looking at Doppler shift in the chromosphere, is illustrated here. Starting with the on-band image in the upper left, and then moving further and further off-band as we go through the images. The higher the Doppler shift, the higher the velocity of the gases. These images were all constructed from the same video data file. I only had to enter different pixel offset values into the software. Another cool output the software can produce is a Dopplergram, which gives a quick visualization of how things are moving in the chromosphere, with blue material moving towards us and red moving away. Notice how we can see the sun's rotation from left to right in the data, as well as how the prominences are moving towards or away from us independent of the sun's rotation. I find that pretty darn cool. As another example, consider this video excerpt from my scan of the near UV part of the sun's spectrum, showing the 2 calcium-2 absorption lines, H and K. Clearly visible are the vertical lines from dust on the slit, there on the left side. But more interesting are the bright flashes that we can see in the middle of the 2 absorption lines. These are active areas, plages, passing across the slit. These bright areas extend vertically as bright streaks across the whole spectrum, what we call faculae in images of the photosphere. We can also see that the two calcium absorption lines extend well past the photosphere, giving us an edge-on view of the chromosphere like we had using the H-alpha line. Finally, you can also see the occasional sunspot passing across the slit, like there's a big one right there. They appear like a large black vertical streak. When we compare the calcium K image produced using the spectroheliograph to that of my 2 nanometer wide filter, the difference is striking. Photosphere details like sunspots are gone, replaced with highly contrasted active regions and a clear definition of the megagranulation that propagates from the convective zone up into the lower chromosphere, a region some scientists call the fluctosphere. What I find most impressive is that prominences, like over here, and filaments, there's one here, there's one here, there's one here, there's one here. They are clearly visible in the spectroheliograph image, something that is extremely difficult to achieve, if at all, with conventional calcium K filters. Another example of things that you can use the spectroheliograph to image is the helium D3 emission line, not absorption, emission line. This is an image generated from the line of pixels corresponding to where the helium D3 emission should be. You can see some very subtle details there, kind of hanging around the sunspots, but there's not much to write home about. If we now subtract this image of the photosphere, constructed by using pixels about an angstrom away from the helium D3 line and doing some basic photo editing, we get this image. Some very funky stuff going on there, including emissions from prominences. There's one there and one over here. Pretty neat. The last cool thing that I have to talk about is magnetograms. This is on my to-do list to figure out how to use my spectroheliograph to generate maps of magnetic strength and direction like the one shown here. Magnetograms were instrumental to scientists figuring out the sun's activity cycle and are still used today to monitor the strength of active regions and to track the transition from one solar cycle to the next. The last thing I have to talk about are the pros and cons of using a spectroheliograph. There are clearly a large number of pros, including an extremely narrow full-width half maximum, uniform illumination of the whole solar disk with no Newton rings, a large multitude of wavelengths to image in, the ability to get good results with less expensive refractors like small achromats, and all things considered, they are relatively inexpensive compared to other alternatives. The SHG 700 is just a bit over $800 US currently. So that's, all things considered, pretty reasonable. From my limited experience, I have identified a couple of cons. For one, the workflow required to get a decent image result is a little bit heavy, with multiple focusing and calibration steps required, followed by a very specific post-processing routine. The steps required are significantly more complicated than what one would be accustomed to using a more conventional etalon or filter-based setup. Second, you need to have a good EQ mount that is able to provide you with smooth slewing in the right ascension axis. Your mount has to be manually slewed at a custom rate in order to scan the slit across the sun's disk and record the associated video. Finally, Lucky Imaging is out. Unfortunately for me, my seeing is typically poor, so Lucky Imaging is my saving grace. This is an image. This is a zoom in of the image that we saw earlier, taken using the double-stacked Etalon. It is a stack of the best 200 frames out of 4,000, sharpened in IMPPG. This is the comparable view taken from the corresponding spectroheliograph image. It is a single scan with only histogram stretching applied. I imagine you share my reaction seeing this result. Yeah! The image quality can be improved, however, by taking multiple scans and stacking them, but it just isn't practical to collect 4,000 scans, process them, and stack the best 200, like I did with the double stack Etalon. A single scan alone, taken with the spectroheliograph, takes about the same amount of time as it did for me to collect 4,000 frames with the other setup. So to realize the full potential of the spectroheliograph, one requires good seeing conditions. So that is it. I hope you enjoyed my talk. I have presented a brief review of the broad range of accessories that are available today for improving your solar observing experience. Most of these accessories can be added to your existing telescope setup for enhanced results. The least expensive layer to observe on the sun is the photosphere, on the order of 10 to 100 times cheaper than the chromosphere. The sun is a dynamic and easily accessible target, well worth your attention. I encourage everyone to give it a try. Thank you.
Okay. I've been checking out. I think we've got all the questions that have come in. There's a couple of comments from people admiring your work and sharing their experiences also. Eric, back to you.
Yeah, I see we have Steve Ibbotson on the watching the show. Steve, I know he does the same kind of thing that you do, Jim. You know, it seems to me that the SHG is kind of like a scanner. I mean, it's like one of our desktop scanners. And basically you're constructing an image line by line by line. So what is the resolution in that case? Does that depend on the speed of your scan, of your mount moving?
So there is a part of the workload that I mentioned is that there's a requirement to match the speed that you are scanning at, so that you're manually panning your mount. You have to synchronize that with the frame rate of your camera, so that the angular distance that's traveled in each frame matches what the width of one row of pixels is in the final image. And there's some tools with the software that helps you to figure that all out. It's not overly complicated. It's just another step in the process. So I'm using is it 10 megapixel camera? The camera I'm using has two micron pixels, and it's large enough to, on a 618 millimeter focal length telescope, it's able to get the whole disk width across the field of view of the camera. That's sort of the ideal setup. And that's actually what the 700 means in the model number of the ML Astro unit. 700 is the focal length of refractor that it's meant to be used with. That and anything smaller than 700, and it works well with that.
So what is your limit as far as, I guess, pixels in one direction for a full disk. Ideally, how many pixels across could you get?
I get about, just trying to remember, it's around 3,000 pixels.
So ideally, under perfect condition, 3,000 pixels will give you a lot more detail than you showed in that last image. So you really are seeing limited.
I am very much seeing limited, yes.
Actually, we're all seeing limited when we do this.
So if I go back to these two images, I don't want to dwell on it too much because my conditions are really bad, and a lot of the other images that you'll see online of people who have better conditions than me, their spectroheliograph images are gorgeous. They're just beautiful detail. But that's not where I live. So this is the same camera used for both of these images. It's just that the advantage of being able to sort through 4,000 frames and pick the best 200 to average them, and then use all of the sharpening processes and deconvolution filters that's in IMPPG, that is what's allowing me to take really terrible data and generate a not so bad image. If I've had those tools available to apply to the spectroheliograph, the image would be, it would be much, much better. And
have you ever taken your SHG images and put them into PixInsight and used some of the sharpening tools like Solar Toolbox or Blur Exterminator?
I have not. I don't use PixInsight, but a couple of the members of my local astronomy club do use it, and they have they've greatly enjoyed and liked the performance of those filters. But I haven't used them, no.
Alex, do we have any more questions online?
Well, I see no new questions coming in. A couple of conversations going on, but that's about it.
Okay, Jim, you can stop sharing if you like.
All right. I can find where that went to. There it is.
Very interesting presentation. Of course, we're all thinking, do we need a spectroheliograph?
Oh, absolutely you do.
Do I need another toy?
Well, my engineering background just can't get enough of this kind of a thing, the tinkering and getting results and the limitless opportunities. Like the magnetogram is definitely on my list. This is totally something that can be done. I just need to figure out how to do it. It involves using a polarizing filter, and I haven't figured that out yet.
By the way, once we end the show, you're welcome to stay on. We usually have a little chat afterwards. But any more questions that popped up? Thank you. Yeah, we got some thanks coming from online. Yeah, very interesting presentation. Food for thought for all of solar imagers.
Eric, we did get a question. Mike, 1959, wants to know if you've got any tips for focusing with the double stack.
Yeah. I don't know what setup you have, but in my particular case, my two etalons are at the front of the scope, and I can very easily disconnect them. So I usually start with a single stack, get it focused, and get it a good image, as evenly illuminated as possible with a single stack, and then I add the double stack. And usually it only needs a small tweak of the double stack tilt adjustment to get it right on. So that works for me. I also find, again, I have the tilt tune that both are on the front, and I align them 180 degrees to each other, and that seems to make it much easier to tune them to each other. Other than that, focusing, yeah, once you've focused with the single etalon, because the image is brighter, so it's easier to focus, I never have to touch the focus again. It's always just the tuning and getting the illumination even across the whole disk is a challenge.
Okay, so
Focusing is the bane of solar imaging.
Yeah.
Is it focused? Is the seeing conditions deteriorated? Do I have good focus?
Yes.
which is it? Oh, it changed there just in that moment. I know, it
Yeah.
drives us crazy.
It's, yeah, you definitely need to have a good focuser with a good slow knob, and then you just back and forth until you zero in on it.
Alex?
Oh, another pointer, actually. I have a little LCD screen that has a little viewfinder on it, and I use it as a second monitor on the telescope or the computer outside. That makes it way easier to do anything. Focus, adjust your etalons, because you can just hold it in one hand and do whatever you need to do. It works wonders instead of trying to see your screen, the sun illuminating everything.
It's when you're pointing towards the sun, you're looking at a computer screen, your pupils are down to the points.
Exactly.
So it helps to get into a dark space. I mean, if you can
Yep.
run a line into a dark space, it makes everything a lot easier. Alex, did you have another comment or question that popped up?
No, the people are offering some suggestions and mostly talking about how they've got a new challenge that they've got to get into, spend some bucks. And Steve Ibbotson suggests that they try altering the gamma setup, I think, in respect to focusing.
Yeah, gamma varies depending on whether it's proms or whether it's surface. Anyway, I think we're kind of done. So, Jim, you can hang with us for a little bit. And
All right.
for all you out there, thanks for tuning in. Next week, some of us are going to be at Nice. We're not going to have a program, and we'll see you the following week to hear all about the trials and tribulations of setting up a remote telescope at Starfront. So, Patrick, you're running the show? All right, take us out. So, good night, everyone.
Nah.
Good.